Working. Yeah, there we go. Okay, cool. All right. So I think we can go ahead and get started if that's okay with you.
Absolutely.
So welcome everybody to the Computer Science Colloquium at Augusta University. And we've had a lot of really good speakers this semester and in the past. And I know one person that has been a participant a lot of the times is Dr. Jonathan Aldrich, who I'm really excited to have here as a presenter this semester. And he's at Carnegie Mellon University, where he does a lot of really cool work in things related to programming languages and software engineering and how we can build more secure and better software. And in this presentation, talk a little bit about how we can make it more usable as well. And so I'm particularly excited about hearing what he has to say. So I think I'll just turn it over to him. And thank you again, Jonathan, for being willing to give a presentation.
Sure, thank you. Can you enable me to share my screen?
Oh, yeah, sorry. There we go. You should be good now.
Right. Perfect. Okay, so thank you very much for the invitation. I'm delighted to be part of the colloquium at CCS at Augusta. As Harley said, I'll be talking about integrating usability into programming language design. I want to mention this is joint work with Michael Koblenz, who is my former grad student, now a postdoc at the University of Maryland, and who will be on the job market this year. So if anyone is hiring out there, please take a close look at his application. He's really, I think, going to be a leader in this area of the intersection of HCI and programming languages. Michael was co-advised by Brad Myers, and Joshua Sunshine, my colleague, also contributed substantially to the work. So this is an exciting time for programming languages. Functional programming is everywhere. That excites a lot of people, including myself. We're seeing popularization of new functional programming languages, things like Julia for scientific computing, Scala with lots of advanced features, languages like Groovy. But we're also doing things like adding lambdas to Java, C++, C#. So lots of I think progress in industrial languages and in new research languages. We're seeing languages with new powerful type systems like Rust that provides ownership types for safe low-level memory management. And we're seeing interesting kinds of verification for complex systems code. So this is enabled by advances kind of at the fundamental level with separation logic and proof assistance, but also other kinds of tools. And so you see examples like CompSert and SEL4 where we're able to verify whole systems artifacts like operating systems and compilers. But the question is, can people use these new programming languages and tools? Rust in particular has, I think, a bit of an infamous learning curve, right? A lot of people give up learning it, and this hampers adoption. I think, it certainly is learnable. And I think once people get to know it, many people really love it. So I think it's a fantastic advance. But there's this challenge, right? And I think we would like to make programming more accessible. And so I think we have to ask ourselves the question, do advanced programming languages harm this goal, or can we actually make them easier, right? Thinking of proofs, proofs are very valuable, but if you look at the data on the effort that went into proving the SEL4 operating system correct, the kernel, or the CompSert compiler, it's perhaps 10 times the cost of developing from scratch without proofs. And it's correct. So we can be confident in the correctness, but at what cost, right? So we need ways to make these new programming language ideas usable so that they have an impact in practice. So you may have some questions about this, right? Is it hard? Can anyone make their programming language usable just by thinking about it a little bit, or do we need fancy techniques from human-computer interaction? Does studying usability produce deep insights, or is this kind of just about nicer keywords? And does it actually make a difference if we get it right, or is it kind of at the margins? So I hope to answer some of those questions in this talk, at least give some answers from our preliminary research. So I hope to convince you that designing a usable programming language with some advanced features is, first of all, important, the effects of making it usable are big enough that they could plausibly influence the adoption of cool new programming language ideas. That it's hard. So researchers, like myself, I'll be my own prime example here, right? Get this wrong all the time. And that it's interesting. It's not just about keywords, but it's also about abstractions and mental models. And this might include a lot of things that may affect your formalization. So if your model of interesting is it affects my formalization, then I'll have some interesting news for you. I'll show how some HCI techniques have been used and adapted to design usable programming languages, and we've seen some exciting results come out of that. And I hope you'll pay attention to language usability research and maybe explore doing some yourself. So the first example I'd like to look at is Glacier. Glacier is a system for enforcing immutability in Java in this case, and it stands for Great Languages Allow Class Immutability Enforced Readily. So as a warm-up, let's get a little bit interactive here. I'd like to see if we can work together to make this data structure interactive. So this is actually it's a slightly simplified version of a data structure we actually used in some of our user studies. So we have a class user. User has a username, a password hash, some authorized files. There's a constructor. There's some getters. The real design has a few other classes and some more accessors, but this will do for today. So let's see. Does anyone have any suggestions? This is just plain Java code. It's not necessarily immutable right now. What should we do to make this class immutable? If you're on, if you're live here in Zoom, just speak up or raise your hand if you want to give a comment. Otherwise, maybe Harley can pass them on, and I'll edit it in place. So let's see. You can tell me what to do. Any suggestions?
I guess they're being shy. Yeah, I'll understand the question. So everyone's online apparently as students, and then we have some people on YouTube.
Oh, it can be. I know it can be.
Yeah.
To speak up when. You want to just talk through it with me, Harley?
Sure. Yeah. So you want to make this class immutable, then we need to try to get rid of assignments within user, right? The constructor.
Yeah, well, of course, the challenge here is we do need to initialize these data structures, right? So
Right.
I think the challenge is we'd like to make sure no one changes the data, largely these fields, and the data in them after we create the class user. So something that like one thing to think about is what does Java provide right now to make data structures immutable?
I forget. I've been programming Java forever. I know in things like Swift, you can say like let and stuff like that instead of var to make it to where it's immutable instead of
yeah. Okay. So
mutable. So I imagine Java has something similar to where I
like
don't know what it is.
So the equivalent of let in Java would be final.
Oh, final, right?
Yeah. So just everyone's got the languages they're familiar with, but Java would be final. So we would add final, to each of these. Now one challenge is, so would this be enough in Swift, for example, right? If you made all of those lets, and you have to think a little bit about, not just these fields, but what's inside them, right? So are strings immutable in the language or not? In Swift, I don't know. In Java, they happen to be immutable, so that's safe.
Yeah, in Swift it is as well.
But here's an interesting one. What about authorized files? So this is an array of strings, and strings are typically mutable, right? So, or arrays are typically mutable. So one of the challenges here is we have to protect the array from being assigned. And so,
Yeah.
one thing we should probably do is make this private. And then no one can go and just like get the array from inside and access it. And that might be a good thing to do for all of these fields.
Yeah, exactly.
Because we're going to make them, accessible via public accessors here anyway. But there's one more thing, which is because this is an array, we have to be careful that when someone passes the array into us, they might have their own copy of it, and they could maybe change it through their own copy, right? So one other thing we have to do is make a copy of this, which we can do with this authorized files.clone.
Yeah.
So then the last to do is we want to get the authorized files here, right? And returning null is bogus. So what should we do here, right? That's like the last question. One thing you might think about is, okay, we could just return authorized files. But that turns out to have the same problem as passing in authorized files and just storing it, right? So we have to make a copy of it.
Yeah.
So that if anyone gets out a copy and then they change it, then it won't. They won't get an error out of that, right? They won't. Someone won't be able to change this. And you can imagine, this scenario is deliberately kind of in a setting where you might care about security. We have a user who has an account on the server, and so immutability is not just maybe a good design, but something we might care about from the perspective of the safety and security of the system.
Yeah.
Okay, so this is where we want to go with this data structure, and so you can see there's some subtleties, right? Some of the pieces like final and private. If you're familiar with Java, that's not too surprising. But some of these other details, like if you have a data structure that you're passing in like an array, you need to make that data structure immutable if you can, or hide it inside and make copies so that any changes don't affect your internal representation. Okay, so that's why this is a challenging problem, right? And we'll see in a bit that people actually get this wrong all the time. But first, let's look at a little bit of related literature. How would you enforce immutability? It turns out people have looked at this problem. They've come up with type systems for immutability. But none of them really solve the problem in a very usable way. And so some of the systems we looked at here are very highly expressive, and actually more expressive than what we finally came up with. But they tend to be a little bit complicated, right? And so there's some trade-offs between the richness of the type system and the usability. So we looked at immutable generic Java, for example, which has polymorphism. That means you can have, for example, a mutable list of immutable things, or maybe an immutable list of mutable things, right? You can also have a read-only reference, which is one reference to an object that is read-only, but maybe other references to the same object you can write to. And you can think about this per object, right? So maybe some objects of a given class are immutable and others are not. So it's very flexible. We started with this, and we made a little extension to it to enforce what's called transitive immutability. But we found that users found the error messages actually in the system pretty challenging, right? And I think essentially, it wasn't like it was a bad set of error messages necessarily, but they were just complicated by the support for polymorphism and all these other features. Many of these systems don't have, they have sort of local immutability. You can enforce that a particular data structure is immutable, but they don't have transitive immutability. So this is like in the example I just showed, maybe the user itself is immutable, but the authorized files is not, right? But of course, if you really care about your whole data structure being immutable, you want transitive immutability. You want everything reachable from the data structure to be unchangeable. And so many systems actually don't support this explicitly. Some of them, there's also just some practical issues like, supporting arrays and so on. we developed a design that was, sort of in the broad sense in the same space as some of these other research systems, and we did try to make it usable, but no other prior system kind of fit this design, with the exception of the D language, which is actually an industrial system, not a research system. And so, why is that? I think the reason is that it's sort of not obvious what combination of features is needed, right? People have played with read-only references and polymorphism and all these other things. What's really important, right? And also what's really required for usability, right? How do you make this actually work, so that people can easily pick it up and understand it and use it correctly? So what we did to try to answer these questions was do some interviews with experts. So, experienced programmers in Java, we looked at people who were developing concurrent programs because, one of the common uses of immutability is to share data safely between different threads. First of all, they emphasized that this was an important problem, right? We asked, caused by state change, and one of the answers we got was, oh God, like most of them. And we had, a number of other kind of comments of that form. There's generally agreement that incorrect state change was a major cause of bugs, and so this kind of motivated some of our initial looking into this, and established, I think, the importance of immutability as a property. We also asked them, are existing mechanisms like constant C++, final in Java, or maybe something like LED and Swift, are they really sufficient, especially in this context of concurrency? And the answer we got generally from our experts was no, that these were too weak. They lack transitivity, which is very important when you're sharing things. It's not just about whether the pointer you're sharing or the thing it points to immediately is immutable, but if you're sharing it across threads, you really need the whole data structure to be immutable. And so, const, for example, doesn't necessarily do that. It's really a read-only reference in C++, for example. And so this focused our attention on, first on immutability, not just read-only references, and secondly on transitive immutability, because this is something that would be stronger and would actually fulfill the constraints that our experts needed. So I think the first insight is you can talk with experts in the field and learn a lot about what property really matters, and then you can focus more on that as a way of getting usability in your system. The second thing, a second major thing we learned from talking with experts was really when we asked them about the granularity of immutability. So what they said was many classes are designed to be immutable. It isn't very common to mix mutable and immutable instances of the same class. And if you think about it, think about the way you might design a set that is mutable versus immutable. You're actually going to have different signatures, right? Mm-hmm. Because taking a union with a union, you might mutate the set in place, whereas if it's an immutable data structure, you're much more likely to produce a new set, right? So the signature is going to be different. The implementation is going to be different. You're actually not going to use the same class for these two things. And so this focused our attention on class immutability, which says that every instance of a class in Java will either they'll all be immutable or they'll all be mutable, right? We're not going to try to have some instances of one and some of the other. And this turned out to be a really valuable simplification, right? It helped us to understand the features of the domain that really simplified the problem in practice. So we put these together and we came up with the following design.
One question I had, Jonathan, sorry, is also, so I'm just curious about the actual interviews too. Like, did you like interview people one-on-one and have a literal conversation, or was it more like a survey style thing, or?
So we did both.
Okay.
I think probably the most valuable insights we got were from the interviews in terms of actually influencing the language design.
Sure, yeah.
But we did have some survey style questions as well to really to establish the importance of the problem. Okay. And then the interviews were delving more deeply into issues that would affect the language design itself.
Yeah.
And so we did semi-structured interviews. So we started with a list of questions that we would ask. But depending on what answers we got, we would, have the ability to follow up and deeper into some of those issues. So it's a pretty common qualitative study technique.
Yeah. I was just curious on how you went there. Thanks.
Right. Yeah. No, it's a good question, and what a big theme of this talk actually is that we gathered a lot of data that actually influenced the design with qualitative methods. And with a qualitative method, you can never be you're typically, asking one or two people, small numbers of people. You're
Yeah.
never too sure that those things will extend, but they do tend to point you in the right direction. Uh,
Yeah. I know this is pretty common in like in user experience design, right? They do these
right.
things and they call them contextual interviews, and they only do like, 10 to 24 people, I think is the usual number. So I
Yeah,
was
we
curious
learned
if
that
it was more in that
well.
flavor. Yeah.
Right. And so at the end we come back and we do more of a randomized control trial, which I'll come back to, that confirms that the design we came up with does work. But
Yeah, cool. Yeah.
how to form it really came from these more qualitative approaches.
Oh, cool. Thank you.
Yeah, absolutely. So a little bit on the design. Here we have an example of some Glacier code. This is just Java, but we're adding some annotations, so we can add an at immutable annotation. And Java just allows you to sort of define these in an extensible way, and then you can define with the Java checker framework, you can write a checker that verifies the code matches the annotations. So here we're saying every person instance is immutable, and you see it's an annotation on the class, so that's our class immutability. And so then if we would assign to a name of a person after construction, then that would be an error. And so in fact, that immutable annotation basically implicitly makes everything final. You don't actually have to write final. You can if you want to. If we go inside the data structure, we would check the elements, and we're enforcing transitive immutability, so we need the string to be immutable as well, and that's okay. But the address is not. Right, so we'd have to fix this code by putting at immutable on address as well, and then fixing any errors that would come from that. So it's a fairly simple design. I think really this is about all there is. The one thing that I would add is for arrays, you put in add immutable on the array type in a similar way, which allows us to enforce immutability for the arrays as well. And that's because with arrays, you don't have separate classes for them. They're just generated by the system as built into Java. So how do we get here? Basically, the user studies with IGJ, which is one of the prior systems we looked at, we did some user studies with them, with people trying to enforce immutability, and people had trouble with these errors, and they basically showed we needed to simplify things. And I think the focus for that simplicity was, first of all, the transitive property for immutability, and then also the class immutability. So that gave us the ability to say, okay, we're gonna basically discard these other features and focus on the things we really need, and come up with the simplest system that would provide that. And then that was followed by iterative prototyping and testing the design for usability. So this is some more qualitative studies where we basically brought people into the lab and observed whether they can address, they can effectively use the system. And when it looks like they can, then we go on and test to see how it actually works. I'll say a little bit more in depth on this iterative prototyping in my second case study, which is on the Obsidian system. But let me talk about whether Glacier was actually effective. So we did a randomized controlled trial with 20 participants. We had 10 each using Glacier and Java. And our first research question was, can Glacier participants enforce immutability better than with final in plain old Java? So each participant carried out 2 tasks, and we measured the correct completion. And one of them was the task that I showed you before, right, with some extensions. And here are the results. So in Java, actually, no one completed it correctly. Okay, so and we actually provided them with a fair bit of training. We gave them a quick reference sheet with Josh Block's effective Java chapter on immutability, and trained them on what they needed to do. But the problem is, with a larger data structure and a lot of details, enforcing transitive immutability is just hard, right? You can sort of get it mostly right if you've been trained, but getting all the details is pretty challenging. And I'm sure someone could have done it, but none of our 20 participants actually managed to do it. Whereas 19 out of 20 of our Glacier participants did. The one who didn't finish because actually, basically you couldn't make a mistake because immutability forced it to be correct if you finished. So and this was a statistically significant result. Another study we looked at was whether Java programmers are more likely to insert bugs. So here we had another couple of tasks and how many people finished the task and how many of the results were correct. And again here, we had seven people in Java finished the task correctly, but 14 finished in Glacier, so twice as many. Interestingly, more people in Java thought they finished. So we had a time limit, and at some point people timed out. And so we did actually reduce the completion rate a little bit with Glacier, but there was an overall win because more people completed the task correctly. Anyway, and these bugs were, it was a synthetic task, but it was one was based on a real hash table code, and we asked people to make it immutable. Another was based on the early find bugs error in the JDK. So these were not exactly real bugs, but they were built on representative code.
Jonathan, real quick, I've got a question for you. This is Paul York. Is Glacier effectively what you've shown, a set of annotations added atop Java itself to effectively make it easier to do the class immutability? Is that kind of the limit of what the tool does?
That's right. Yeah. Just focused on immutability.
Okay, great. I was just making sure that there was not a part that I had missed in there. Thanks.
Yeah, sure. So we also did a couple of case studies as well, just to see, can you apply Glacier to larger examples than these small case studies? So we took some immutable collections from Google's Guava library, and we're able to kind of verify immutability within them. There were a couple of interesting things regarding applicability. So one of the things we gave up was polymorphism. I think our overall experience with the Guava library basically confirmed what we learned from the experts, which is that in general, you don't need polymorphism, but we did in one place. And so there was one method where we couldn't express it because we didn't have polymorphism as written. But if we duplicate the method, then the same functionality is there. So this is a trade-off, right? We certainly could have added polymorphism, but at a substantial increase in complexity. So maybe duplicating a method here and there is not a bad thing to exchange for substantial usability. Anyway, just something to consider. There was one other issue where we couldn't leverage a cache that was used to convert collections to lists, and that's because caching technically violates immutability, but it's kind of a harmless form of that. And certainly one could imagine an extension that would support that. So I think that's definitely, future work might consider supporting that kind of thing. We also took an existing application, the ZK spreadsheet. It's maybe medium size, 57,000 lines of code. I guess maybe that's big for programming languages, but small for software engineering. It took about 20 hours to express immutability in a bunch of places within this. We did, as an example, we created immutable cell styles. That seemed like a logical choice. And this actually led to identifying a couple of previously unknown bugs, but we didn't have any significant issues expressing immutability here. So just an example. And all of our materials for the case studies and user studies are available as part of a replication package. So you can have a look at them if you're interested. So some takeaways from this part. Getting usability right is hard. I think anyone could design a system with the right features for usability. And in fact, one industrial system did. D, as I mentioned, has an immutability system that's almost exactly like what we developed. But interestingly, none of the prior research systems did. And so I think, I don't want to call the prior research failures, because I think they discovered some interesting things from a language point of view, but they didn't at least demonstrate usability. And I think some of the issues here are, not picking the properties that are important in practice, or maybe adding too much complexity to the system. And of course, we didn't test them all for usability. We wanted to have a first result that says, oh, we can build an immutable system that is usable. So I think there's lots of room for exploring other combinations of features that would achieve kind of both usability and usefulness. The other thing is that it required some key insights, and maybe we could have gotten these other ways, but we certainly found that HCI techniques like interviews and iterative prototyping were very useful for getting these. From this experience, we developed a more general approach for usability in programming language development. It's called Pliers. We have a Kai article coming out on Pliers. I think it just came out, or excuse me, not Kai. That's the conference. It's the journal Tokai. But basically, what we did for Glacier was starting with some user-centered needs assessment, right? Interviews and surveys to understand the need for immutability. Some design conception. So here we did some initial development of a core calculus for Glacier. I didn't really show that. Glacier's, programming language theory is not super sophisticated. It mostly echoes prior work, which is why I haven't really emphasized it. But we did do some math and some modeling to make sure we got things right. We did some natural programming, kind of asking developers to write down constraints on immutability, how they think it should be written. And we use that as one input into our design. We used some ideas like cognitive dimensions of notations to try to analyze, the space of solutions. These are basically heuristics that for developing notations like programming languages that can help you think about what the effect of one choice versus another might be. And of course, we also did some analysis in comparison to prior work here. And then there's this iterative process of design refinement where we did a combination of basically formative usability studies and prototyping of a compiler that eventually led to the final design we had, which we tested with a randomized control trial and some case studies. So this is a technique we tried for Glacier, but we also applied it to another example, which I'll outline here. And this one is a little bit more rich. Immutability is a fairly simple type system. We wanted to see if we get a little more aggressive with interesting types, and we apply it to a whole language design. What more can we learn, and does this methodology extend? So here, Obsidian is tackling smart contracts. Smart contracts automate transactions between parties that don't necessarily trust each other. They tend to be tamper resistant. So you might have a blockchain backing a smart contract system that would record transactions and allow people to verify that all the contracts were followed. But smart contracts can be buggy, and too often they're buggy. So the one famous example was the DAO reentrancy bug, in which $50 million was stolen, and to try to recover it, there was a hard fork of the blockchain, very disruptive. There's a lot of other examples involving things like lost assets. A contract takes in assets and you can't get them back out because it's written badly in some way. And so we developed a system called Obsidian, which is a safer smart contract language. It uses type state to mitigate misuse bugs. Type state basically says there's a protocol and you have to call methods of this contract in certain order. So many contracts have some kind of order associated with them. And then linearity mitigates lost asset bugs. So linearity says that if you have a resource like money, it can't be created or destroyed. And so these two type system mechanisms helped us to increase safety, but we wanted to see, can we build a usable system as well along with that? So here's an example of Obsidian. This is a tiny vending machine. It has a coin bin. and the tiny vending machine it's a contract, and it's also an asset because it has money inside of it. So our coins are owned, which means that the tiny vending machine, has the money represented by the coins. Our tiny vending machine has two states. It can be full or empty. If it's full, then it has a piece of candy in it, which is the inventory, and that is also owned. It's another asset. The empty state doesn't have any inventory. So this is indeed very tiny, just one piece of candy. And we can have transactions like buy. So buy, the current tiny vending machine, this is implicitly a parameter here. And I guess it's explicitly written, and we're going to have a state transition from full to empty. When you buy, you have to pass in some coins, and those coins are going to be owned by the caller, but when the function returns, they will no longer be owned by the caller. So this transition of owned arrow unowned basically means that we're passing the coins in, and they're not going to be returned to us. What will be returned to us is the candy, is the owned candy in a return value. So how does this work? Well, we'll deposit the coin that's passed into the coin bin. We will take our results candy out of the inventory. We'll transition to the empty state, and we'll return. And so you can imagine, you can see how this matches the protocol, right? Our coin was deposited, and so that's why it went from an owned state to an unowned state from the client's perspective. And our owned inventory, we passed it into the result and returned it. And so the Obsidian type system will make sure that we actually did take the candy out of the inventory, for example, before we transitioned to the empty state. Otherwise we'd have lost candy. Okay, so we gave users some studies with this as well. One task we gave users was a little bit more complicated than the empty coin bin, but still not terribly complicated. People in the blockchain ecosystem like to think about smart contracts for things like auctions. So here we have an auction, and there's a seller participant. We might have several states in this contract. So its initial state is open. Then once we get some bids, we keep track of the maximum, whoever bidder is winning right now, and also their max bid. And they pass in the money when they bid. So when a bid is made, then we actually have some money inside the auction. And then at the end, it goes to a closed state. And then there's some transactions. So we have bid, which is we actually ask people to complete the bid function. We also have a finished bidding, which is when someone wins, right? So if we check to make sure that we're in the bids made state, and if we are, then we transition to close, but we make a payment to the seller in the amount of the max bid. So the challenge to our participants was, let's implement this bidding function. We have the auction, we have some money, we have the bidder who's making a bid, and if we don't have any bids yet, then we just set the max bidder to this bidder, and we get some money, and we transition to bids made. Otherwise, if we're in the bids made function, then what we're going to do is, well, we're going to decide, how to set this, how to reset the state variables of this auction. And so again, there's a couple of things we ask people to do. Well, what happens if basically they fill in the blank, right? If the money is, if the money passed in is greater than the current max bid, then we want to replace the maximum bid. And otherwise, we want to say, nope, sorry, that bid won't win, and you can have your money back. So, all right, so I have another little interaction bit here. If someone is brave enough to suggest some changes, what should we write for these to-dos? There's a little hint in the corner that says to transfer money, you can call receive payment on a participant. So yes, any suggestions?
So I guess in the first part, you'd have to, do we have to set the max bidder to the person making the bid that's the amount that's bigger than the max bid?
Mhm.
And then we have to set the max bid, right?
That's right. We'll set the max bid, and that'll be just the money that came in, right?
Right. Yeah, exactly.
Okay, good. And then in the else clause, what should we do here?
I'll see if anybody else wants to answer.
Any other suggestions? Yeah. All right. So one hint here is that I've said this is how you transfer money in this particular in Obsidian, and so someone actually passed us money, right? And our signature says it won't be owned by them after this call, but we have to get it back to them some way. And so we'll actually let's see, it's the bidder who's making this current bid that we need to give it back to, right?
Yeah.
Bidder dot receive payment, and we just give their money back to them, right? It didn't work out, right?
Yeah, exactly.
Okay, good. So this makes a lot of sense. The Obsidian's type system, though, will have one problem with one piece of the solution, right? I don't know if anyone has seen it, but what we did here was we assigned max bid to the money that's coming in, but there was already some money here, right? And that money got overwritten, and so we've actually violated linearity here. And I sort of deliberately moved us on to the second problem. This is, you can see how it's very easy to kind of miss this, right? And so actually the very first thing you want to do here is go to the current max bidder, right? And have them receive payment of the current max bid. And then we make sure we don't lose money. So, okay, so Obsidian will have some kind of error, basically, not with this code would type check correctly, but with the prior code, it would say basically, at this point right here that there's a problem, right?
Yeah.
So anyway, that gives you an idea of how the linearity checking would work. So let me go ahead and go back to, yes, okay, so I think that's the same thing we wrote. Yep, I have my sample solution here. Okay, so that's the final design. It gets you a little bit of a feeling for it. Let me talk about how we got there, because this is actually pretty interesting. Our original design, we knew we had both ownership in the system, so we could track money, and also state tracking, and we realized that these two are related to one another, right? Because actually, you can only statically track the state of an object if you own it. Because if multiple people have a reference to it, maybe one could change it and the other people wouldn't know about that change, right? So this is a conventional design, and the design of prior systems that I've developed had basically something like this, right? We'd say an owned tiny vending machine at full. And this is a very conceptually clean design. To our knowledge, all prior systems supporting both separated them. But we found that this had a disadvantage of complexity. And so, one sample user comment when we did studies, asking people to tell us what code did, sample code did, or we would teach them the system and ask them to write the code. And people said things like, I haven't seen types that complex in an actual language enforced at compile time, right? Maybe this is not a Rust user, but we're kind of at the Rust level of complexity here. depending on your point of view. So it turns out that this separation isn't actually needed in our type system. And the reason is because of this very way that they're tied together. If we're tracking type state, it really implies ownership. And so we actually took away the need to annotate owned on things that had a type state. And this turned out to be actually a lot easier to teach to participants. In some conceptual world, there still is some orthogonality here, but in the world of teaching people to program and giving them feedback, this simpler system seemed to help quite a bit. So the insight here is that refactoring the technical ideas enable us to give users a simpler conceptual model, and that was valuable in getting Obsidian to the place where we could teach people to be productive with it quickly. Here's another change. We had an original annotation for passing money to a function was just to say the coin is owned. And the default is that if you pass in an owned coin, then you're giving permission to the system. And then we had another system for maybe the rarer case where money is returned to the caller. So you could say a borrowed coin. And there are prior systems that have borrowing. So this is a design that was, again, kind of foreshadowed in the research literature. But we got feedback from users saying this is confusing, right? When I annotate this as owned, I'm not sure if I'm making a variable owned or if I'm transferring ownership.
Yeah.
And so our revised design basically makes a change in ownership explicit. This arrow idea, right? And we still use coin at owned for money that's returned, but the idea is if you see the arrow, that means ownership changed. And if you don't see it, then it didn't change, right? Which fits more with the design of existing type systems, which generally track things that don't change. Yeah. So the change in permission is explicit in the notation. And we had seen both of these options in prior work. We'd actually used the arrow notation for type state before, but now we know which is more usable, which we didn't really before, right? And I think the insight here, again, is to make the notation match the user's conceptual model.
Yeah.
One more, we looked at how to initialize or transfer asset fields during state change. And we came up with an obvious functional approach where when you transition to, say we're transitioning from the full to the empty state in this tiny vending machine. You basically, in the constructor for the state, you can initialize the fields. And if there's any assets that need to be returned, you sort of return them from this. So I think that was a natural kind of conceptual model, but the notation, it does look a little funny, right? Why is the state transition like returning something? And people were confused by this. We also did a natural programming study, and we asked, if we don't give them a design, how do they expect it to work? And we just, described it to them and asked them to write, what code do they think expresses this? And what they all did was initialize the fields before the state change, right? They got everything in the right state to make the state change, and then they made the state change at the end. And so we have in our revised choice, you actually assign state variables before transition, either setting them up like assigning to the coin bin, or taking things out beforehand, and then the transition is just an atomic thing that confirms it all afterwards.
Yeah, it kind of reminds me of like, I don't know, for some reason it makes me think of like how people usually structure like denotation and stuff, right? It's like do all like your assignments first and then boom, run to some other function.
That's right. Yeah. So so this is, and it also fits with the idea of with object invariance or data structure invariance. There's places where they hold like at the beginning and the end of a function, and then maybe you violate them in between, right? Yeah,
exactly.
So again, I think we once we figured out what the user's conceptual model was, we could make the notation match it. Okay, so we did do a study here. I'm going to try. I'll see if I can finish a few minutes before 2, so I won't talk a lot about this. But
I mean, it's fine. We started a little late, so
okay.
Yeah.
Well, so a few things we did to make the study, I think, useful. First of all, we tried to choose tasks that were, of interest in the community. We'd seen, smart contracts aren't like super widely used, but when people write simple examples, they tend to write auctions and prescriptions and casino and things. So we had one task of each of these. We actually spent 90 minutes training people because we had to teach them a whole new programming language. And actually, we taught them either Solidity or Obsidian, and these are people who didn't know both beforehand. So both languages were kind of on an equal footing there. But an important piece of the training was we weren't just having them like read through a document. It was active learning. We had them carry out tasks. So that was important, we found, to make sure they actually paid attention. We did a lot of piloting of the training and tasks, make sure they're not too easy, not too hard, and recruiting appropriately. So we actually, for this, we recruited master's students who had some prior experience, certainly an undergrad degree, sometimes some work experience as well. And we did a Java knowledge screening test. They had to get 4 out of 6 or something on kind of knowing Java. And then we did a couple of studies. One was basically, is this actually usable? And we found that 6 out of 6 people were able to complete the auction task with Obsidian. So I think this shows we actually were able to teach the basics of the language pretty effectively. We also did a randomized control trial comparing Solidity and Obsidian. That was 20 participants. And here we had only 2 out of 10 Solidity participants completed the auction task correctly, whereas 7 out of 10 Obsidian people did. So I think this is an illustration that, first of all, our type system eliminated a lot of bugs because most of the Solidity participants actually completed the task. 9 out of 10 completed it, but mostly they had some bugs. Whereas the Obsidian participants, actually 2 of them didn't finish, so we slowed them down a little bit, but not very much. And we almost everyone did it correctly. There was one person who had a bug. It didn't involve losing money. They gave the money to the wrong person. So, we're not verifying everything in this particular system. It's only a type system, not a verification system.
Yeah.
So we did have some very positive results. Obsidian participants were able to complete the task more correctly. It isn't all roses. So we did several tasks here, and the results were a little less conclusive because we ended up running the auction task first, and then the others were subject to time available. But the casino task was a little bit more creative. People had to actually, develop their own state machine for the casino and match it to the state of the game that people were playing inside the casino, and that was actually harder for people. So I don't know that we've demonstrated yet that Obsidian is usable for more creative, in-depth design tasks. I hope we could do that, but I think it will require more training and practice. And we already were doing 4-hour studies, so that's a challenge going forward to kind of push that to the next level.
Yeah, and there it could be hard just because like getting people's heads wrapped around the problem and then not knowing the language. Because for me, like personally, I'm just thinking about like, in order for me to kind of creatively explore, I got to really know the language well so that I can like more concentrate on the problem rather than thinking, how do I translate this? And
right.
So I imagine it might have been some cognitive like dissonance that's like happening that might have caused things to slow down, I guess.
Yeah, right.
Yeah. Interesting.
Yeah. So, okay, we did a case study with Obsidian as well. This one is parametric insurance. It's a kind of insurance that the World Bank is exploring. They work with us a little bit in third world countries. Basically, in a third world country, you don't want to do what you do in the US and have an insurance inspector come and examine the field and see, that the crops didn't grow because, you don't have enough money to pay the inspector. The field is too small, and there's a lot of lack of trust. So parametric insurance basically says, if the weather's bad, we'll pay. And so it all depends on, reporting of the weather. It gives people a certain amount of predictability in insurance. And so that was an example of like trying to solve a real world problem, not just these small kind of artificial examples. We also did a case study we implemented this policy in both Obsidian and Solidity, and this is just a small piece of it, but you can see that Obsidian is shorter overall. That the version in Solidity has to do state tracking manually, whereas we build in Solidity. And they end up having to put in some explicit state checks, which are basically built into our type system in Obsidian. And also, we ended up seeing a lot of kind of repeated initialization code in Solidity that we could avoid in Obsidian. So there was just a little flavor of the differences kind of on a more in-depth task. All right, so let me go back to the high level points. I think, designing usable type systems, and we were mostly focused on type systems, but I think programming languages will probably follow the same trend. Is challenging, right? I think you're not your own user most of the time, and understanding what users really need can be hard. And in general, there can be a conflict between interesting properties and expressiveness and usability. And so I think historically, we sometimes make poor design decisions if we don't study usability explicitly. I think we have a couple of examples here of how HCI techniques can augment our typical toolbox. Some of those new tools include interviews and surveys, and this natural programming technique, as well as usability evaluation of prototypes. I think for me, this complements our existing work, right? PL theory is still important. Optimizations and implementations are still important. And partly that's because it's actually the technical properties that make the approach useful, and we want both kind of usefulness and usability. Mm-hmm. So I think, but we did find that there were some insights that at least I think were deeper, right? That kind of link these technical abstractions to human concepts. Understanding the key properties and features of the domain, like transitive immutability, like states and assets. Refactoring technical ideas to give the user a simpler mental model, but one that's still sufficient to do what you need. Combining permissions and type state was one example. The transitive immutability notation was another example of a simple abstraction that kind of gave a powerful property. And then making the notation match the conceptual model, as in, for example, owned, arrow unowned, to denote a change in ownership was another thing that we did. So with that, oh yes, and finally, we can see some significant wins, right? The randomized controlled trials, they're certainly focused like a laser on, the issues we were trying to investigate, but at least when those things come up, we can see major differences.
Yeah.
So yeah, with that, if there's any other questions, I'd be happy to take them.
Yeah, thank you. That was great. Any questions from anyone?
Hi, I have a question. Sorry I came a little bit late. And thank you for the talk. So my question is about immutability part. So when it comes to say like transitive immutability, is it like, because as I understand, it should be something non-forwardable, because that makes it verifiable. That's what makes it resistant against the tamper-proofness kind of thing. So when it comes to transitive immutability, like what does it actually mean? I'm trying to understand. And the second question is, in all of these use cases or the systems that you show that you use case study, there was a block diagram or survey kind of thing. So is it more about those systems? Is it more about decentralizations, or is it more about immutability? Because immutability can still be guaranteed without being decentralized. So for all these blockchain based or smart contract based system, which one is, like, I would say, is the most preferable or most useful for systems like these?
Right. Okay, good question. So to take your first question, the point of transitive immutability is that a data structure can be made of multiple structures in the heap, right? And in an object-oriented system, that's very common, but really in any system, you might have layers of data, right? Collections of within collections. And so transitive immutability says the whole data structure, the top level object and everything inside of it is immutable. And so it's a strong property, because it says if you share any piece of the data structure, it'll be immutable. And you don't have to worry about someone changing it. if that might be a security threat or if it might, be an error with respect to concurrency or something. For your second question, it's true. For example, we compiled, well, the blockchain will also enforce certain properties, right? A blockchain that builds in money like Ethereum will track who has what money, and at the system level, it won't be duplicated. The problem is when you write code, you often have data structures that track the amount of money that you have, right? And those can get, and so you might, from the perspective of your data structures might be different from the perspective of the underlying blockchain, right? So the blockchain, if you have a market, then you might have or a bank, you might have a notion that each user has a certain amount of money in their account, and so you want your internal accounting to match the external accounting of the blockchain. And that's where some errors in asset loss in smart contracts can come in. The blockchain knows who has the money, but your accounting might be messed up in a way that, where you expect to be able to give some money back to someone and you can't.
So would it be appropriate to say that the immutability is more important than the decentralization for most of these systems that you studied in your survey?
Oh, I don't want to necessarily make a statement about importance. I think decentralization is a super important property of blockchains. I wouldn't want to give up that. But when we run contracts, we also want them to be correct. So I think it's really a situation where you need both.
Yeah. Okay. Thank you. Thank you so much for the presentation.
Thank you.
Yeah, there was a couple questions on YouTube for you. So
excellent.
One is it possible for any errors during is it possible for any errors during state transitions? That is, when we transition from owned to unowned and an error prevents us from restoring the state, maybe?
Yes, good question. So we are not, Obsidian doesn't have so Obsidian has, I believe, a rollback construct, which is the same as you see in some blockchains, right? If a transaction fails, the semantics is that you roll back to the state before it. And the semantics of Obsidian is if you roll back a transaction, then everything transitively that called it rolls back as well. And so that gives a nice clean semantics for errors. I think it is an interesting question. If you wanted to support a more structured and maybe more flexible system like exceptions, you would have to specify what happens to ownership and type state, when an exception is thrown. But for Obsidian, the answer is fairly simple. If the only error is a rollback, and in that case, everything goes back to the beginning. If you want to encode other kinds of errors, you could encode them by, returning data structures, I guess. But yeah, it's interesting. With type state systems we built in the past, you sometimes need to do things like express conditionals, and that's something we haven't built in Obsidian yet. But if I return true, then you have this thing is owned. If I return false, this other thing is maybe it's not owned, right?
Yeah.
So that's something that some of our prior type state systems have done, and we don't yet have data on whether that's usable or how it can be made usable. So I think lots of interesting work to do.
Yeah. A second question they had was for usability / reducing the overhead of adding the state transitions explicit, what are your thoughts on separating the possible state transitions out of the code?
What are the thoughts on expressing the state transitions out of the code? Can you say that again? There's like
Yeah, sure.
again.
So it says for usability / reducing the overhead of adding the state transitions explicitly, I think they meant. What are your thoughts on separating the possible state transitions out of the code?
Yeah, that's a good question. I think, people who use a library that has state need to know what the state transitions are. And so documentation tools that can extract those and put them in documentation is useful. We've actually built such tools and used it to evaluate some of our prior work on type state, again, for usability. There's also an aspect of Obsidian that I didn't talk about. At one time we explored an example where the transitions that you can take in a state are actually members of that state. So they're nested within the declaration of the state. And that seemed very intuitive, but there are some, but it was intuitive in some ways. But if you have a method like that and it actually transitions to another state, then like when you're halfway through the method, you might be in a different state than the one you're nested within. And so I don't know if this is, maybe it's related to the question a little bit, but we actually took the transitions out of the state so they could have sort of an outside perspective on the states, which seemed to be more reasonable and more understandable by our users in the presence of transactions that made state changes.
Yeah. So they can see the specification better, I guess.
That's right. The specification was more clear in that case by taking it out of the individual states.
That makes sense. Awesome. Okay, well, I think that's all the questions. And thank you again, Jonathan. This was really great. Yeah, this is. I think your presentation was even better than I thought. So I've got a lot of ideas now spinning in my head. So this is pretty great. Thank you very much.
Thank you so much for inviting me. That's been great.
Cool. Have a good day, and thanks everybody for coming.
Thank you. You too. Take care.
Yeah. Bye.
Bye.